we can start. Ready?
Yeah.
We are live. All right. Hello, everyone. Welcome to today's new episode of Corecast. I am your host, Tim.
Mikey.
And this is Sahil. Welcome, everybody, to a brand new, exciting episode of Corecast. Before we get started, a few logistical things, as we always say. If you haven't already, do join our Discord channel so you can ask us questions there. And if you're watching this on YouTube, where we try to do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, ask us questions during the episode, and we'll get to them as well. So, without further ado, let's get to it. So this episode actually germinated, if I said that correctly, from a question that a viewer on a previous episode asked us, something involving gravity and how it doesn't fit well into particle physics. And we'll get to all that later, use terms like non-renormalizable, but asked a very technical question. And we took it upon ourselves to try to explain this topic of why gravity and quantum mechanics, as it stands right now, don't fit as nicely together based on the standard model of physics. So we want to break that down and explain like why. So I guess like Tim or Mikey, can we start with like how do you guys think about the current standard model of physics? Most people think of it like, oh, that's like the state of the art of particle physics, but is there like a broader way of thinking about it?
Yeah, maybe I can take a stab at it. So the current accepted theory of particle physics is the standard model, and you can argue that it's one of the most well measured theory in existence right now. We have tons and tons of measurement of all the variety of particle masses, their energies, and their interactions. And what it comes down to that is so the standard model it's a little bit like chemistry. It's basically a reductionist views of all the interactions, at least most of the interactions that we know. It tells you that there exists a handful of fundamental particles and how their interactions are. And these interactions are kind of like chemical rules. Like imagine you mix oxygen with carbon, you make carbon dioxide. And in the same vein, the same spirit, it tells you things like, hey, if you mix an electron and mix it with a photon, the electron could move, right? And so on and so forth. So this is a list of rules, and in some ways, these rules have some what we call coefficients or some numbers in front of them, and those are tuned to kind of fit to the experimental data. So you can kind of think of the standard model as a bunch of kind of a list of rules that are adjusted to describe our experimental data, and in such a way that it's very efficient. You know, a mountain's worth of data can be explained this way. These small sets of rules and their coefficients, if you like. So that's the standard model of particle physics currently.
To give it an analogy real quick about that, would you say that like we can think of the standard model of particle physics as kind of like this cosmic cookbook, for lack of better words, where you have like the ingredients are particles, like the different food items, and the instructions are kind of the way in which things interact, and that's like the end product of what you get? Or is that analogy not as apt?
It's a good analogy. Yeah, it's like a cookbook for how things can be combined. But like it's much simpler than the periodic table. I guess to elaborate on that, like the coefficients that Tim's talking about are things like essentially boil down to the strength of the interaction. Like how strongly do two particles interact with each other? How strongly do they influence each other? These are determined by parameters in the theory, which we call coefficients. And that's pretty much the entire contents of the theory. It's what kind of interactions can happen and how strong are those interactions.
Yeah.
Real quick, Mikey, just to kind of zoom in on what you just said in terms of parameters, can you give an example to the audience based on like high school physics of like parameters that you see that appear in the standard model and how they describe strength of interactions?
Yeah, sure. Like you know that like if you take a magnet, it will have some strength with which it's attracted to a piece of metal.
Mm-hmm. You muted yourself.
So like how strong is this attraction that's set by a certain like a number, which we call a parameter or a coefficient of the theory.
Got it. Got it. Go ahead, Tim.
Oh yeah, I was just gonna say, Mikey, I think you got muted slightly. Maybe we.
Oh, I was getting a call. I had to ignore it.
Okay,
Yeah,
no
yeah.
worries. Let me just reiterate on that. Yeah, and those coefficients you can kind of loosely think of them as sort of like a propensity of or a probability of events happening. For example, in this cookbook, there's some coefficient on how likely an electron and a photon is a particle of light, for those who don't know, how likely they will mix together and something could happen. So and if that number is small, then when you mix a photon and electron together, maybe chances are that they're just going to pass through each other. Nothing will happen. And if that coefficient is large, then it becomes more likely that the electron will get affected by the photon. And for example, the electron might absorb the photon and move, or it can hit the photon and they can scatter. So those are possibilities. So the coefficient kind of governs that.
Gotcha. Gotcha. So, okay. So, from what I understand, taking a step back, you're saying that the standard model is essentially made up of these like ingredients of these, what we believe are fundamental particles and how they interact. And these interactions are described, and strength of interactions are described in terms of like the value of these coefficients, is just as you just mentioned. Is that correct?
Yeah, that is correct. And I think one thing to keep in mind in this cookbook analogy is that I mean, some people might think, oh, it's so obvious. Of course, there's got to be a cookbook, but it's not necessarily the case, right? Like, imagine you see a really fantastic looking, I don't know, like a wedding cake that's really well built. It's not obvious that you can spend a few hours and mix some eggs, flour, and sugar and somehow make that, right? Maybe just
You say wedding cake?
yeah,
Oh, okay.
yeah, like a really elaborate wedding cake. I don't know, like a fancy dish, right?
Uh,
But what if the cake just, I don't know, fall out of the sky? Maybe there's no way to make it from simple ingredients. That's possible, but the brilliance of the standard model is that all the fancy combinations of things can be reduced by simple ingredients, simple interactions, and when you mix together in some predefined a fixed number of predefined rules, you can cook up fantastical things. So that's really the power of the standard model and the philosophy behind it. It's why it's useful.
So, with this analogy that you just said, are you saying the beauty and brilliance of the standard model of physics is like if I see a cake anywhere, I'll know what the fundamental ingredients of it are, like eggs, flour, and other things that go into it, no matter like where it comes from. For instance, like if it's made in like France or if it's like made here or in any other country, like I know like what the ingredients are. It's not like if I go to a different country, it's like a completely wildly different set of ingredients.
Yeah,
yeah, no matter which country you go to, wedding cakes are always made from protons, neutrons, and electrons.
That's fair. That's fair. So I guess like also taking now a step back, we've described the standard model of physics. Maybe we can like go over to actually before we go over to gravity, is there an advantage of describing standard model in terms of these coefficients? Like you brought up the notion of coefficients rather than just stopping at particle interactions and the particles that make up the standard model. Is there any like way in which you're framing this argument?
You go first,
That's
Pat.
it.
Yeah. I mean, that's an interesting question. I mean, I don't know. What would you say, Tim? Like, it's how do we end up with this theory of rules and numbers? Like, yeah, we have rules that determine how particles can interact, and we have numbers that determine how strongly they interact. And this is kind of like a very minimalist way of describing everything. Did
yeah,
it have to be this way? Yeah, I mean, is it
yeah.
an accident?
I think it's through a pragmatic approach, right? Like we have experimental data, and the goal of science is to explain these experimental data. But of course, I think every physicist you talk to don't think that the standard model is the end game. The standard model does have this feeling of it's a little bit ad hoc, right? It's a bunch of rules, but it's a very
Mhm.
great first step. It's able to describe all the experiments, but we don't really have a way to explain where do those ingredients come from, where do
Mhm.
those, I don't know, like those interactions come from, and indeed physicists have tried very hard to kind of go to take this leap of faith to go one step beyond and say, well, hey, maybe we want to get more information on where this cookbook comes from. Maybe there's a master chef, like a master theory, that's able to derive all these rules for the cookbook. And I think that is the goal, I think, in physics, to figure that out. But we don't have that yet. It's a pragmatic
Mm.
view. We just don't have, a better way to describe these things other than a very succinct set of rules, I think.
Yeah, it just happens to be that if you have a list of rules and a list of numbers, if you have this, it allows you to predict everything that we see. That's a little strange, right? The fact that I'm not even talking about like where the rules, where the cookbook came from, but the fact that the cookbook is even structured like this, and the fact that that seems to work to just grab everything. I mean, one might even say that that's kind of surprising, right?
Yeah,
Maybe it's similar to the surprise that you mentioned before.
yeah, exactly. It is really surprising, actually. Like, imagine you go into the lab. Let's say you grab 4 electrons and you move them around and look at the way they interact. It's not obvious that these interactions can be explained by simpler ones. But it turns out that if you just look at the interactions between, let's say, 2 pairs of electrons, then you can kind of add them up and you can obtain a coherent pictures of how 4 electrons can interact. And you can go extrapolate a little further. You can ask, well, how do 5 electrons interact? 6, 7, or you can mix in more and more particles, and then you can explain complicated phenomenon like, oh, why does an electron orbit an atom? You can break it down into individual quantum mechanical interactions. Oh, there's photons emitted by the nucleus that gets absorbed by the electron. It happens, I don't know, every microsecond or whatever, continuously. If you add them all up, you get this picture of at the atom, right? The fact that this is possible, it's not obvious, but it turns out that it is possible.
That's interesting. So you're saying that a really complicated interaction between like, let's suppose there were like 20 electrons. I can basically break it up into pairwise interactions between 2 electrons and just sort of sum them up and eventually get like what that interaction looks like. Is that what you're saying?
Yeah, yeah, and keep in mind that that actually can only be done approximately. I think we have to remember
Mm.
that from our previous episode that every physics model has a regime of validity, and that's the
Mm.
true for standard model of particle physics. This procedure works within some boundary, within some energy range. For example, as long as the electrons aren't like super powerful. For example, as
Mhm.
and then this prediction will be okay as long as the energies are low enough that we can extrapolate. But sometimes if we happen to go beyond this regime of validity, our predictions could be very wrong. For example, if your electron beam has so much energy it creates a black hole, well, we really don't know what happens. But as long as the
Mhm.
energy is low enough within the regime of validity of the standard model, then everything is good.
Gotcha, gotcha. So I want to take a pause on the standard model for right now and move over to gravity. So can you describe like I guess like what is your conception of gravity? Because I mean everyone knows it is the thing that just keeps us on Earth, planets orbiting around the sun and kind of how the universe like moves in some sense, like the dominant force. I'm wondering, is there like another way of thinking about gravity? I'm gonna go to Tim first.
Yeah, I think.
Gravity special.
Yeah, I mean, gravity is special, but also it's actually also not that special. I think a lot of people
Mhm.
think that, oh, a lot of people learn about this. Maybe they read Brian Greene's book, or popular science articles, and they always talk about the conflict between gravity and quantum physics. But really, if you look at this lens from particle physics, what is gravity? Gravity is just the introduction of a new particle called a graviton, just like a particle of light, photon. And in that lens, graviton can interact with, and because gravity is universal, anything that has mass or energy can interact. So graviton can interact with electrons, graviton can interact with protons, quarks. It can even interact particles of light. It can interact with photons. So from that lens, it's actually, pretty well understood. Many of these interactions, like a electron could absorb a graviton. It could emit a graviton. The Earth is emitting graviton so that it attracts us. So from this lens, there's actually no difficulty to use quantum gravity to explain most of everyday's phenomenon.
Mm-hmm. Wait, do you mean just regular gravity, or why quantum gravity? Like, I could just use Newton's theory of gravity to explain most of the stuff we see, right?
Yeah, that's more like phenomenological. But I think what Tim's saying is like you can this idea we have of like everything, every force, every interaction is due to some kind of particle interacting with each other. It's not difficult to include gravity in this quantum picture where things are described by particles, like discrete particles propagating.
Oh, I see.
Yeah.
That makes sense. So then I guess then where exactly is the difficulty? If I can just put it in, like, problem solved, right? What's like the hard part about this?
Yes.
I think this goes back to what Tim was saying. When Tim was talking, like this idea that you can describe complex things by building up from many simple things.
Yeah.
Like if you have like lights, 5 light scattering, you can imagine this as 2 by 2 like pairwise interactions. Well, when you attempt to describe complex things from simpler things, oftentimes that requires going to a smaller distance, right? If you want to explain a complicated cake by looking at the atoms inside of it, it requires you to like zoom in to a smaller and smaller distance to see these larger numbers of simpler components. And that's where you can run into trouble when you really try to zoom in and does this picture make sense when I zoom in all the way? Like if I have, 2 particles scattering, maybe I can imagine that scattering, if I zoom in there, is like, some kind of flurry of other interactions, maybe even of the same kinds of particles. But then how far can I zoom in and maintain this picture? If you try to do that with certain theories, that's where you run into trouble.
Tim, can you elaborate on that a bit more?
Yeah, I think the issue is very technical. At the end of the day, it's that the math doesn't work out, but we can intuitively try to understand why the math doesn't work out. One issue with gravity is that gravity is universal. It's always attractive, right? And on surface, you might not think that's a big deal, right? Electromagnetism, it's attractive, sure, why not? But remember this: in electromagnetism, only things with charge participate in it. So it's a little bit more compartmentalized. But for gravity, graviton can attract light. Light bends under gravity. Gravity attracts electrons. In fact, gravitons attract other gravitons, right? So imagine you're trying to do this process of breaking down complex interactions. Let's say I want to study the interaction of 2 gravitons, 1 photon, and 2 electrons, something like that, right? Something pretty complicated. And I want to zoom in and see, well, can I use the methods of particle physics, break them down into pairwise interactions, try to explain it with something simpler. Then I kind of run into this trouble because if I zoom in, I see that, hey, 2 gravitons coming together, they could emit another graviton. But gravitons themselves have energy and momentum. And from Einstein's theory, that, well, not Einstein theory, but just we know that gravity is universal. This graviton itself can attract other gravitons. So when you go to the rabbit hole, you see that, hey, if you zoom in, actually, you can't just break them down. Gravitons can create more gravitons, can create more gravitons, can create more and more and more and more gravitons. And then this picture of I mean, you can still try to brute force your way through it. You can say, hey, let me just say that let me just say this 5 particle interaction. How do I explain it in terms of simple interactions? If you try to do that, it turns out that you get actually you have to sum up infinite number of things.
It actually gets more complicated as you
Yeah.
zoom in.
Yeah. So then this extrapolation becomes useless now, right? Like you're trying to explain something complex by something simple, but that simple thing turns out to be infinitely many things. Then you might as well just go to the lab and measure that as opposed to trying to explain it because it's not useful anymore. So that's
By the
real.
way, like it doesn't mean that the picture is not true. Like, like we know that we can take a complicated scattering of, like, let's say electrons, and we can describe it in terms of simpler components. In this picture, if we try to do that with gravity, we try to explain something complicated with simpler components, we find that these simpler components are actually more and more complicated. And we lose our ability to kind of make predictions from it. But it doesn't mean that that picture is untrue.
Yeah.
It's just a jumble of gravitons, and you can't really calculate anything. But I think there's every reason to believe that that picture still holds.
Yeah. And I would also emphasize that the same picture actually also exists for electrons, right? Let's say you want an electron and a proton interacting. You could also expand this and see that there's so many complexity. Oh, the electron could emit a graviton, the graviton could, emit a photon, whatever, right? But it turns out that the math tells you that those interactions are a lot smaller. So we can kind of ignore them, right? So in normal particle physics, the law is that well those complications can be ignored systematically. But for gravity, you can't, it turns out. So that's the difference between gravity and ordinary forces. And it has to do with the universal attractive nature of gravity.
Huh. I guess I mean, could you make this same argument for like even electromagnetism, that like if I take like two electrons coming in and let's say they exchange like a photon and they, bounce off each other, and I were to like zoom in more and more into that interaction, eventually that reaches a point where I can't extrapolate. It's just that you're saying that the interaction is like, I guess, like, is weak for that happening, or how do I think about that?
I think that's correct, right? I think in normal day life, the
Hmm.
energy is so low that those more
Hmm.
complicated stuff is very
Hmm.
small. Keep in mind that standard model is an approximation. Like all these calculations are approximations. So when those complicated terms are very small, you can just ignore it. And actually, the same thing happens in gravity, right? Like when we're attracted by the Earth, there isn't quantum gravity involved, right? Like
Hmm.
those terms are also small. But it's just that when we're trying to explore, let's say, graviton interacting with graviton, in order to observe that to begin with, you have to have very large energies because gravity is really weak. In order to beef up gravity, you need more energy because more energy is more gravitational interactions. And the moment you beef up that energy, it turns out that all the complicated pieces also get really large. So that's kind of
Hmm.
screws you up. I mean, the same thing happens to electrons too. If you shoot electrons at the energy high enough such that electron can create black holes, then of course gravity also comes in. I mean, gravity is so universal that every interactions, when you have enough energy, it kind of messes you up, right? So this is kind of like how would I put this? Maybe it's almost like a dead end for this process of extrapolation, right? It's like an endpoint. But like, hey, look, all the niceness of having a cookbook kind of goes out the window when faced with these extreme scenarios.
Hmm. I see. I see. I'm just sort of thinking like in the case, what am I trying to say? Uh I'm trying to see if there's like another is there another like way to give an analogy for this, for instance? Like, is there anything in like everyday experience where this can apply as well?
Ooh.
That's rough. Well, I think we talk about this.
Yeah.
So the essence is this idea of extrapolation. I mean, we can think of standard model as a massive, like an imagine you're trying to predict, let's say, the population of the Earth, right? You can just say, oh, you know what, with the rules of statistics, you can kind of draw a line and say that, well, right now is 1.5 billion. Maybe in the next few years it will go up to 2 billion. You can make that prediction. But of course, you won't be able to make that prediction and say, well, 1,000 years of the on Earth, how what do we think the number of people will be? If you continue this extrapolation blindly, you might get something nonsensical, right? If you just exponentially extrapolate it, maybe you'll get like 10 trillion. I don't know, right? Wouldn't be sensical,
Mhm.
right? So the standard model works because the theory is able to extrapolate, and maybe I don't know, maybe stock market is a good example, right? Like if you limit yourself to a particular stock, I don't know, like technology stock or whatever, you can say, oh, you can roughly extrapolate that it goes up reasonably, right? Maybe that's electromagnetism, and maybe the strong force will be some other stock. You can predict with, maybe not very well, but there's some with some
I don't
uncertainty.
like the stock example. It's like it's too random. I think it's like with population, right? Like if you try to
Yeah,
extrapolate population linearly, right? You can say, okay, it's increasing this much now, it's going to increase this much. But in order to do that, you have to ignore a lot of other factors, right? Like there could be resource caps that will make the
yeah.
population level off. But this extrapolation only works if there are things you can ignore and you know you can safely ignore them. Then you can simplify the picture and extrapolate.
Yeah,
But gravity kind of a situation where we know the details are important.
yeah. Maybe gravity is like the stock. Maybe in some ways, gravity you cannot do that because
Yeah,
we don't know the underlying physics. So even
yeah,
though there
it's just too
is,
complicated.
yeah, there is physics, but you can't just extrapolate. You kind of have to know, you know, yeah, you kind of have to know exactly what's going on in order to make that prediction. I think that's the problem with gravity.
So one question I have is around like you mentioned gravity is very weak. And so like in electromagnetism, it's the interaction coefficient is also like fairly small. Why is it not the case if I were to like naively look at it that gravity can't apply the same to gravity? Why is it that like is it just that like like why do you need to go to a higher energy is kind of actually there's two questions in one. Why do you need to go to a higher energy? And like naively I would think that it's weak, like I can ignore the self-interacting nature of it, or like I could break it apart.
Oh yeah,
Yeah.
totally. Yeah. I mean, for every day, yeah, we can ignore those. But if you want to know what happens when it's strong, then
Mm,
um, yeah, for everyday interactions, like you don't need like you don't need quantum gravity to calculate like any kind of gravitational interactions. But if you want to ask extreme questions, like what happens when gravity gets really strong, um, we can do that with like electrons because we can observe that force becoming strong in everyday life. But
mm.
gravity never really gets strong unless you're close to a black hole or something.
Yeah,
So it's just so far outside of our
yeah.
control.
Let me just add, Sahil, your observation is actually one of the biggest theoretical problems in particle physics. We actually don't know why gravity is so much more extreme. Why it's so weak compared to other forces. Why we have to go to such extreme in order to see these gravitational interactions. Uh, this is one of the biggest mystery in particle physics. Why is gravity so different in that way? And I don't think we don't have that great of an answer actually.
Yeah.
Yeah, yeah, actually, regarding that, when you say gravity is weak, what does that actually mean? Like, why is it that if I go to higher and higher energies, gravity suddenly becomes like strong? Like what that yeah, just like how are those two related to each other?
I mean, I don't.
Well, I guess the simplest way to like just quantitatively, right? If you have two electrons, you bring them to a
Mhm.
certain distance, and
Yeah.
they feel a certain force of attraction, right?
Hmm.
if you want to get if you want to get two neutral particles to feel that same force of attraction at the two electrons feel from gravity,
Oh, you
you would
mean
have to
repulsion, right?
huh? Oh yeah,
Two
yeah,
electrons are
repulsion.
repulsion.
I'm sorry, electron positron then, yeah. But
Okay.
just the strength, the magnitude of the force. For
Yeah, yeah.
gravity, you would have to get them like, you know, a billion times closer just to feel that effect. And in order to get them a billion times
Mm,
closer, you need to pump a lot of energy to get them that close.
mm,
Yeah, and I would say it's not obvious why the strength of certain forces gets stronger or weaker as you if you go to higher or lower energy. Like we have the
It's
strong
actually really weird.
yeah, it's weird. Yeah, we have the strong force, the electromagnetic force, um, and the electro weak force and gravity. I guess theoretically the strength of these forces could increase or decrease as you increase
It
energy.
all depends on how complicated the jumble gets when you
Yeah,
zoom in, right? The reason why the strong force gets weaker when you get farther away is because of like when
yeah,
you zoom in, the self interactions of all those
yeah.
little
mm,
pairwise
Yeah,
simple components.
yeah, exactly. The counter example is the strong force. It actually gets weaker as you pump in more energy, which is very strange. And,
uh,
and gravity doesn't do that. I mean, you can argue that it's because of the universal attractiveness of gravity, right? If there's some
mm,
anti-gravity stuff going on, maybe you could imagine that the attraction can cancel out, and somehow when you go to different energies, the attractiveness could decrease or increase. But we don't see that. So far,
mm.
everything is attractive. So gravity just adds and add and add and add. But it's very strange that it's so weak these days. You would imagine that because everything is attractive. Why wouldn't gravity be so strong all the time? But it's
That's
not.
how we
Mhm.
get it. Even though everything is attractive, it's still so weak.
Yeah, it's very strange. But there are some arguments that says that if gravity was strong, you could argue that maybe everything will turn into a black hole, and then it would be a
For
terrible,
sure.
yeah, it would be a terrible universe to live in. Certainly, there wouldn't be humans. So you can make that maybe it's a selection bias, but maybe that's not good enough. So there's a lot of argument in that. It's very complicated.
Huh. I
It's
mean,
still
could
broken down into just like so in electromagnetism you have plus and minus charges, and that means things can be neutral, and that means there's stuff you can ignore. With gravity, there's no such thing as neutral, which means you can't ignore anything, which means that if you want to calculate something, you have to take everything into account. Um, every
mm,
other force that we know of has this property that it can achieve a state of neutrality, which means that we
Hmm.
don't have to like consider everything.
mm. Does that mean if we found like, let me use in quotes, anti-gravity, then
Yeah,
like that would mean you could maybe do something similar? I don't know if that makes any
probably.
sense.
Yeah, like yeah, if there was so like if you could combine matter in such a way that the gravity was zero, that just
Yeah.
cancel each other out, that we wouldn't have any of these problems.
I mean that would be incredible. We could what? Well, I mean, I don't it seems unlikely to happen. There are theoretical problems with that because negative mass usually means instability, blah, blah, blah. But if
Mm,
indeed there's kind of like a gravity charge analogous to electromagnetism, there's like positive gravity and negative gravity, then yeah,
mm.
you can just grab a negative gravity vest and we just flow straight into space. I mean, that's like science fiction, but that vest probably will be so unstable because it will interact with air molecules, the earth. It will probably just emit gamma radiation, just kill anything that goes near
Uh,
it. But but who knows?
yeah, actually, one question I have is like to your point of gravity being so weak, it still seems, at least when I learned cosmology, that's like the dominant force like in cosmology. Like you don't really look at electromagnetism, you don't look at this. Is that because things are neutral or like,
Yeah,
yeah,
exactly.
just
Yeah,
ignore
Yeah.
all
that's
that?
why. Yeah, everything else cancels out as you get larger, but gravity just builds and builds and builds. So it's like a brute
Mm,
force.
gotcha. That makes sense. So we are almost at time. I wanted to give you guys any final parting words you'd like to say to the audience about maybe like what's in the future. Where does that leave us? I'll leave it up to you guys.
I don't know.
Go,
Maybe
Mikey.
I would just want to rage against the popular belief that like gravity can't be quantized. Um, It's absolutely not true. I think the particle picture of gravity makes perfect sense. You know, the fact that you can't make predictions and you can't calculate things, I think does not negate how sensible this picture is. You can calculate gravitons scattering off of each other. It's just not a very useful thing to do. Um, yeah, I guess that's it.
Real quick, Mike, you said gravity quantized. What does that mean?
Like
Like,
you can describe it as a particle.
okay, okay,
Yeah.
okay.
There's a lot of people who believe that gravity is so special that you should just never try to think of it as a particle.
Mhm.
Um, and or maybe it somehow indicates that this picture of everything as particles might just be like a piece of the truth and not the whole truth. And that could be
Mm.
true, but um, I just think that all of these arguments are coming from kind of a disingenuous place because there's absolutely nothing wrong with modeling gravity as particles. It's just that um, it gets complicated. Is the issue?
Yeah, I suppose I'll add to that, continuing this theme that physical theories usually come with a limit, come with like a little asterisk, like terms of conditions, right? And 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 I think particle physics exemplifies that. It's not trying to fool you into thinking, hey, particle physics can apply to all cases, right? Like particle physics is what we call an effective theory. It knows its own limits, and there are things that are not explained, the parameters are not explained, but yet it's very predictive. It helps us understand many phenomenon, right? So it's not. I know there's a lot of popular science article that says, oh, groundbreaking stuff, breaking, particle physics is wrong. New physics discovered, stuff like that. Um, but I just want to add that, like, physicists are preparing for that. Basically, particle physics itself, the standard model itself, is not complete. We know that we want a better, more complete theory, and we're still waiting for that. So I don't think people should be surprised, let's say in the near future or whatever, that says, hey, uh, particle physics was wrong or whatever, because it was never fully correct in the first place. um, but of course, it doesn't mean that it's useless. It's still extraordinarily useful. And the same applies to quantum gravity, right? Like we have some theories of quantum gravity, but it's effective. It's not a full theory. For now, it's only able to explain very basic things like why the Earth attracts us from a particle perspective. It doesn't do very much more. It's just not very useful. But it doesn't mean that it's wrong. It just means that we're still missing a fully consistent, or at least a little more consistent, theory of quantum gravity than what we have right now. So I would say, yeah, stay tuned. Like physics, the theory itself is predicting its own demise. So, so we'll get there someday.
That is definitely hope. And so to kind of go back to the title of this episode, how to break particle physics, is the answer just introduce gravity?
It's already broken. I think it was never unbroken. or smash things at higher energy, then you start seeing very complicated things that cannot be predicted. So
Fair enough. Fair enough. Well, on that note, I want to thank everybody for joining us, and we'll see you all next week.
yeah, see you
Hey,
all next
guys.
week. Bye.